Number 12. Thermodynamics. Thermodynamics is the branch of science that deals with the concept of heat and temperature and the interconversion of heat and other form of energy. Thermodynamic system is assembly of very large number of particles having a certain value of pressure, volume and temperature. Everything outside the system which have a direct effect on the system is called its surroundings. The quantities like pressure, volume and temperature which help us to study the behavior of thermodynamic system are called thermodynamic variables. The mathematical relation between the pressure, volume and temperature of a thermodynamic system is called its equation of state. For example, the equation of a state of n moles of an ideal gas can be written as PV equal to nRT. In thermal equilibrium with each other if they are at the same temperature. So if a system is said to be in thermodynamic equilibrium if it is in mechanical equilibrium, means net force and net torque acting on that system is equal to 0. Second criteria is it is in thermal equilibrium, that means its temperature and equal to temperature of other system for with which it is in thermal equilibrium. And third criteria is in chemical equilibrium, means rate of forward reaction is equal to rate of reverse reaction. Equilibrium of a system, its macroscopic behavior or macroscopic variable like pressure, volume, temperature describing the thermodynamic state of the system do not change with time. The macroscopic quantities which are used to describe the equilibrium states of a thermodynamic system are called state variables. The value of state variables depends only on the particular state, not on the path used to attain that. A thermodynamic system PV diagram is given and this system undergoes certain process. Then pressure at point 1 is P1 and volume V1 and temperature T1. Then to go from state 1 to 2 it may take three different paths. First path is this one, second is this and third this. So in different path they may take different amount of heat and system may do different work in different path. So amount of heat and work done are not state variables because these two are depending on path taken by the system. But pressure, volume and temperature are state variables because at initial point pressure, volume and temperature are P1, V1, T1 respectively. Then at final point all are going to have certain value P2, V2 and T2. It is independent from the path taken by the system, whether it is following or path 2, that means whether system is following isothermal process, adiabatic process or isochoric process. At final point their pressure, volume and temperature are independent from path taken. So we can say that pressure, volume and temperature are state variables. Thermodynamics. If two systems A and B are in thermal equilibrium with a third system C, then A and B are in thermal equilibrium with each other. According to this law, temperature is a physical quantity which has the same value for all systems which are in the thermal equilibrium with each other. Two boxes are there. One is of cubical shape and other of spherical shape. In spherical shape box, oxygen gas is there and in cubical shaped box carbon dioxide is there. Both are in equilibrium. If it is given that both are in thermal equilibrium, then both contain different type of molecules, but since they are in thermal equilibrium, so they have same temperature. So we can say that temperature is something which is independent from the amount which contain in a system. It is same for all system. It is independent of whether that system contain some gas and other system contain some other gas. If they are at same temperature, then one thing is common to them, and which is temperature. So temperature is independent from the quantity which is inside a container. It's same for two container having same temperature. The internal energy of a system is the sum of molecular kinetic energy and potential energy. For an ideal gas, internal energy is only kinetic energy of that gas. Static process. A quasi-static process is an infinitely slow process such that system remains in thermal and mechanical equilibrium with the surrounding throughout. In such a process, the pressure and temperature of surrounding can differ from those of the system only infinitesimally. That means why this quasi-static process is important. Why we need to make a process so slow. Why we can't make a process which is fast. Because in fast process there will be a loss of energy. So system can uh, reach at the same initial, which is initial same temperature, pressure and volume. You can consider this situation. Suppose a spring is attached with a mass m, and if you drop this spring from compressed state, then after few oscillation this spring will remain at some position, remain at rest at some position. But you just consider one forward step and one reverse direction of motion of this spring. Even in one complete oscillation, this spring is not going to come at the same position, because if it move fast, then air drag will start acting on it, and we all know that air drag or viscous force is directly proportional to velocity of object. So object is moving fast, then more viscous force or more air drag will act on it. And air drag is non-conservative force which cannot store energy. So there will be loss of energy, and this spring is not going to come at same compressed state, because some energy will be lost in air drag or viscous form. Okay, so if you want this spring to come back at the same position, then you need to do this process slowly. If this process would be slow, then air drag acting on this will be tends to zero, because air drag or viscous force is directly proportional to velocity. So for slow process, we can say that no air drag or negligible air drag act on a system. So system can come to its initial state completely. Now hope I that you understand this concept very clearly, that why a quasi static process is required for a system. To go from one state to another state, many processes can be possible. Actually, infinite number of processes are possible, out of which four processes are important, which we are going to learn in this chapter. First one is isothermal process. So a process in which temperature remain constant is called an isothermal process. Adiabatic process, there is no exchange of heat through system or surrounding, which means system will not interchange heat with surrounding. volume remains constant is called isobaric process. A process in which volume remains constant is isochoric process. A graphical representation of the state of a system with the help of two thermodynamic variables is called Stator diagram of the system. The graph between pressure and volume is called PV diagram. Expansion or compression of a gas. When the volume of gas changes from V1 to V2, the work done is given by formula pressure into change in volume. If graph between pressure and volume is given, then you can find area under pressure volume graph to get work done. And if some equation are given, then you can integrate pressure with respect to volume equation to get work done. For cyclic process, to find work done from PV diagram, you can find area under that cycle, right? Area under that cycle. If that cycle is clockwise, then that area will give you positive work done. And if that cycle is traced anti-clockwise, then you will get negative work done. It states that if heat dq is given to a system, a part of it is used in increasing the internal energy by the system, and du, that is du, part of which is used by system is du, and remaining energy is used in doing external work dw. It is just a restatement of law of conservation of energy. Sign convention used. Heat absorbed by a system is positive and heat given out by a system is negative. Increase in internal energy of a system is positive and decrease in internal energy of system is negative. Work done by system is positive and work done on a system is negative. An isothermal process is given by formula W equal to nRT ln V2 by V1. Process work done when 1 mole of gas expands adiabatically and its temperature falls from T1 to T2 is given by W equal to R divided by gamma minus 1 in bracket T1 minus T2, where gamma is ratio of specific heat capacity at constant pressure and at constant volume. Near the room temperature, the molar specific heat of most of the solids at room temperature and constant volume should be constant, is equal to 3R. And if you put value of R 8.31, value of R is 8.31, then you will get its value 6 calorie per mole per Kelvin or 25 joule per mole per Kelvin. This statement is known as Dulong and Petit's law. Heat of gas at constant volume. It is defined as the amount of heat required to raise the temperature of 1 mole of gas through 1 degree Celsius at constant volume. Molar specific heat of a gas at constant pressure. It is defined as the amount of heat required to raise the temperature of 1 mole of a gas through 1 degree Celsius at constant pressure. Relation between two specific heat of gas, that means specific heat capacity at constant pressure and at constant volume. This relation is Cp minus Cv equal to R, where R is universal gas constant. Device which converts continuous heat energy into mechanical energy in a cyclic process. It essentially consists of number one, a source of heat, second, a sink of heat, third, a working substance. It is the ratio of useful work done by the engine per cycle to the heat engine energy absorbed by heat engine. That means how much work is done by that heat engine, and to do this work how much energy is absorbed by that heat engine. Ratio of these two quantities is defined as efficiency of heat engine. So mathematically efficiency of heat engine will be equal to W upon Q1, where W is work done by the engine and Q1 is heat taken by this engine. Amount of heat from source and it gave Q2 amount to the sink, that means to the surrounding, then it must have done Q1 minus Q2 amount of work because energy is conserved. So if it has taken Q1 heat from the source and given heat Q2 to the sink, then remaining amount of heat must be utilized for work doing by this engine. So we can write W equal to Q1 minus Q2. So formula for efficiency become Q1 minus Q2 upon Q1. Is it okay? Yes, of course, it's absolutely okay. So there are two statements of second law of thermodynamics. First statement is given by Kelvin Planck statement. He says it is impossible to construct an engine which will produce no effect other than extracting heat from a reservoir and performing an equivalent amount of work. That means it's not possible to construct an engine which take given amount of heat from source and completely do work of that given amount, right? It must throw some energy to surrounding. So there must be some loss of energy. Second statement is of Clausius statement. It says that it is impossible for a self-acting machine unaided by an external agency to transfer heat from a body at lower temperature to another body at higher temperature. That means without taking energy, without taking help of any other source, a body cannot transfer heat from lower temperature body to higher temperature body. It's not possible to transfer heat from cold to hot body. A process which can be made to proceed in the reverse direction by variation in its conditions, so that any change occurring in any part of the direct process is exactly reversed in the corresponding part of reverse process is called a reversible process. That means suppose a system undergoes a process and from initial state P1 V1 T1 to final state P2 V2 T2 in suppose this direction, in one direction, then if it come back to the same position, same state, and also by following same path should not be different. If it come from different path, then that type of process will not be considered as reversible process. Reversible means forward path must be retraced exactly, each and every point should be retraced exactly. Then only we can say that process is reversible. Irreversible process. A process which cannot be made to proceed in the reverse direction is called an irreversible process. Ideal heat engine which is based It is an ideal heat engine which is based on Carnot reversible cycle. Its working consists of four steps: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. Engine is given by eta equal to 1 minus T2 upon T1. Efficiency of normal engine is given by eta equal to 1 minus Q2 by Q1. And in Carnot engine, you can replace this Q2 divided by Q1 to T2 upon T1. That no engine working between two given temperatures can have efficiency greater than that of the Carnot engine working between the same two temperature. And second statement is the efficiency of the Carnot engine is independent of the nature of working substance. A heat engine working in the reverse direction. Here a working substance absorbs heat Q2 from the sink, that is cold body, at temperature T2, and external agency does work W on the working substance. This work W. A large amount of Q1 is rejected to source at higher temperature T2. In this case, body will take heat from a object which is at lower temperature, which is inside a fridge, you can consider it, and it will eject heat to atmosphere which is at higher temperature. So to take heat from lower temperature and eject it at higher temperature is not a natural process. So it required to be done some work on this engine. This external work is our input, and we use this refrigerator to cool a cold object which is already cold. So its purpose is to take amount of heat Q1 from cold substance. So output of this substance will be this Q2 because we are using it to take heat from a body at lower temperature. Again, suppose you have kept something inside a fridge and you want to make it more cold. So this refrigerator will pull out some heat. This heat is taken as Q2 and external electricity is doing some work on it, and this is ejecting Q1 amount of heat to atmosphere. So why we are using this refrigerator to take Q2 from object. So Q2 is our output, our motive input, which is work done by electricity. So here output by input is Q2 divided by W, work done. So output by input here is not called efficiency, it is called coefficient of performance in case of refrigerator. Of heat this refrigerator is pulling out from refrigerator or freezer, and W is amount of work done, then these two energy must be equal to heat ejected by this system. So Q2 plus W will be equal to Q1. So you can write W Q1 minus Q2. So you can replace this W to Q1 minus Q2, right? And if engine is Carnot engine, then you can replace this Q2 to Q1 and Q1 to T1. So in place of Q2 you can write T2, and in place of Q1 you have to write T1, right? This engine, this type of formula is valid only for Carnot engine. If engine is normal, it is not Carnot, or this refrigerator is a normal refrigerator and it's not a Carnot type, then you cannot replace these Q1 and Q2 to T1 and T2 respectively. For normal refrigerator, you just have to write coefficient of performance equal to Q2 divided by Q1 minus Q2, or Q2 divided by work done. To study only this much in this chapter. Wish you all the best for your exams.